let us continue with support vector machines. If you remember, we wanted to find a W and V, B the slope and B value of a plane, which will correctly classify all the points and give the highest margin. So, we formulated it as an optimization problem. We converted it into a dual form, where the dual problem can be written like this: the W alpha, which is the Lagrangian, is summation of all the alphas, the Lagrangians, Lagrange multipliers, and half times double summation. So, this is double summation I equal to 1 j equal to 1 alpha I alpha j y I y j x I dot x j, which is same as x I transpose x j, subject to all the alpha i's being either 0 or positive, and the summation alpha I y I being 0. So, this is an example of a quadratic programming problem, and we can solve it always and get a set of values of alpha i's I equal to 1 to n, plug in those values in this equation, which we already got as the value of W when we minimize with respect to Lagrangian with respect to W, and we can find the value of W. We have also seen that you can actually write it as a matrix form, where if you consider the Hessian matrix, consider the Hessian matrix H, which we construct as follows. We have x 1 to x n, we take all pairs of x I x j, all pairs x I x j, and the ijth entry of the Hessian is nothing but the class level of ith point, class level of jth point, the vector of ith point dot product the vector of the jth point, which is same as x I transpose x j again. So, this way constitute the Hessian, and we similarly consider another vector of the Lagrange multipliers and another vector u, which is all one vector n one's vector. And if we do this, these equations can be, I am writing down in a simpler form, is Lagrangian, which is W also, I write here as W, is the Lagrangian vector u minus half Lagrangian vector a Hessian matrix Lagrangian transport subject to alpha I greater than equal to 0. Okay. So, this is a typical quadratic programming problem, and if we solve this, there are numerical methods to solve this. If you solve this, what we will get is this is how we will solve. I am telling you about this is how we will solve. You get many numerical techniques like sequential minimal optimization, interior point method, which will solve this and give you a set of values of alpha i's. Okay. And as I have told, you can get alpha I to reconstruct your W. Okay. But the most interesting part of this is that if you solve, most of the times if you note that see your n can be large, n is your size of the training set, it can be large. So, you can have large values of n, say 1 million, 1 lakh or something. So, your Hessian matrix is really big, n by n, really big matrix. So, actually computational complexity of solving this QP problem is little high. There are ways to reduce it. So, if we solve this and find out the values of alpha 1 to alpha n, you will find most maybe 95% values. We have a restriction that alpha I should be greater than equal to 0. Most of the values actually turn out to be zeros, exactly zeros. Okay. So, if you have 1000 n equal to 1000, maybe 990 examples. Note that one thing you also note in this regard is that, see, I have as many Lagrange multipliers alpha i's as many training points as the number of training points. So, there is a kind of correspondence for every training point x I, I have a corresponding Lagrange multiplier alpha I. So, every Lagrange that comes here also, when you write down the constant, it comes that for every x I there is alpha, and most of these alpha i's will be 0, as I have told you. I mean, if you actually solve it, you will observe it also, and few of the alpha i's are greater than 0. Now, we are naturally curious, since every alpha I correspond to x I, which are the x i's for which alpha i's are 0, and which are the x i's, the training points, for which alpha i's are greater than 0. Okay. So, let us try to answer that question. The answer lies in this theorem called the Karush-Kuntaka theorem. Okay. Also, another thing you quickly note is that see this W is a summation of alpha I y I. So, if an alpha is 0, the corresponding y I x I does not contribute to the value of W. Okay. So, corresponding x I y I do not contribute, only the few alpha i's, I said few alpha i's are greater than 0, only those few x i's y i's contribute to the value of W in computing the value of W. Okay. So, let us see which are these. Okay, let me state you a theorem known as the Karush-Kuntaka theorem. KKT, Karush-Kuntaka theorem. What the Kuntaka theorem says is that, so you see, you have two problems, a primal problem and a dual problem. What we optimized in the primal problem is minimize half W transpose W such that y I for all I, if you remember the definition. And what we did in the dual problem is that introduce Lagrange multipliers and simplified the constant, made the objective function more complex. So, we had a objective function which are slightly more complex. Sorry. One. So, the constant, basically the constant moves to the objective function, and this is and this is I equal to 1 to n, and the constant was so that is why the duality. See here, see the constant goes to objective function, whereas a simple constant here. So, now okay, so this is also actually greater than equal to 1, because for one point it will actually be the minima. Okay, one point it will actually be the minima. So, let me, for sake of clarity, So, now this constant, so what this optimization business basically is about. So, if you look at say for example, WB space hypothetically, and this is the objective function L that we are minimizing, the constant sort of defines a feasible area within which we should search for the solution. And what we look is that the objective function gives a takes on a value within the feasible area, wherever objective function is minimum, that is our solution. Okay. Now, this constant can be satisfied in two ways. One is greater than 0, one is exactly equal to 0. Similarly, here greater than 1, equal to 1, equal to 1. Okay. So, the idea is like this: when the constant is satisfied as an inequality, basically your solution is in the interior point. Okay. And your solution is equality, constant is equality, your solution is a boundary point. So, this is an interior point, interior solution, and this is a boundary point. Similarly, here what the KKT theorem says, of course, I am not proving it, you have to accept it. If you open any optimization book, you will find it. So, what the KKT condition says is that the interior solutions in the dual problem correspond to boundary solutions in the primal problem. Okay. And the boundary solutions in the of primal problem correspond, the interior solution in the primal problem correspond to the boundary solutions in the dual problem. So, that is the duality. It is the duality. Okay. So, but if you remember from our previous slide is that we said that we basically the weight is nothing but this . So, we are interested only those alphas which are greater than 0, basically not equal to 0, because it is only those alphas which will contribute to my W. Only those alphas will contribute to. So, we are interested in these alphas, and we also mentioned before that they are a very small minority among all the alphas, the one which are not 0, they are a very small fraction of all the alphas. So, if n is 1000, there will be only 10 maybe. Okay. So, it is this which is really important for us, these alphas. Okay. So, excuse me. So, by duality, this interior alphas correspond to the boundary xi's. Note that every alpha has a corresponding xi. So, basically we are doing a alpha I to xi mapping. We are doing a alpha I to xi mapping. Okay. So, we are actually interested in these particular xi's, which give yi into wt xi plus b as 1, So, if you okay, I have used up all the board, I have to erase it. Keep this picture in mind. equal to 1. Now, yi is either plus 1 or minus 1. So, if it is equal to 1, this quantity should also take on a value 1. Okay. See, the magnitude of this quantity should be 1. If you remember what we did, we defined when we defined margin is we said distance from xi to the line and we said that minimum of this over I is we normalize w and b to make it 1, that is why we get a margin of 1 by norm of w. Okay. If you remember the earlier thing, we scale w and b, each multiply both w and b by a quantity. Note that the distance does not change because both numerator denominator I am multiplying by the same factor. So, distance is same, margin value remains the same. The numerator of the margin by scaling w and b can be normalized to having a smallest value of 1. So, basically this point correspond to the smallest value of this quantity. So, when does this smallest value appear? The smallest value corresponding to the xi which is closest, w is same for all points. Okay. So, only these xi's, and there may be actually multiple xi's which are closest. So, only these xi's will have alpha I greater than 0, the closest one. How to again find this closest? As if we take the line and parallelly spread out two lines on both sides, increase, increase, increase. So, you sort of take this line, then do this, then do this, you spread out, and when you touch one of these points, stop. You stop when you touch one of these points. Okay. So, if I redraw, I will get a picture like this. I stop. Okay. So, there will be no other point in this gap, and this gap would be called the margin of the lines of the line. And the points which lie on this boundary, would be called, would have a alpha I, as I have said, they will have w xi, w transpose xi plus b equal to 1, absolute value equal to 1, and they will have a alpha I greater than 0, and they will only determine w. This critical, and they are a small fraction expectedly. These critical values would be called the support vectors. Critical points would be called the support vectors. Okay, let me redraw. In fact, this is twice the margin, margin is only this much. These and these are the support vectors. The points which just touch the margin, they are the support vectors, and they have the property that B equal to 1 for them, and they also have the property that the corresponding Lagrange multi is greater than 0. And this line, the slope of this line rather, I can express as xi. In fact, since except support vectors all other alpha is at 0, I can rewrite this summation as I is a support vector, only the other I can drop off the other alpha i's. I can consider only the support vectors, only these points, this point and this point, and sum of their Lagrange multiplier y I x I get W. Okay. So, how do I get my B? It is very easy to get B, because I know for the support vectors this holds. I know my W, I have computed W this way. I pick up a support vector, I know this equation will hold, I know W, I know xi, I will find out B from this equation. So, I will equate to 1, from 1 minus W xi will be the B for a support vector, any support vector I can pick up and find out B. Okay. So, let me summarize the steps. Oh, by the way, this line which is actually the main thing of our interest, which has this margin, is called a optimal separating hyperplane. Or a support vector machine. Okay. We already know how to get W of that point. It is take all the support vectors, sorry, take xi to be a support vector, sum of these values. How do I find B? I know B equal to 1 minus W transpose xi. I know W, I have already computed, where pick up any support vector, okay. To summarize, so Hessian matrix actually contains all the information you get from the data point, no other place it is used. Find all the support vectors. So, support vector is all the xi for which alpha is greater than 0. For all the support vectors, add up this. Can you tell how do I classify a new point? Let us say call it xj. How do I classify a new point? Very simple. What I will actually do is that I will find the sign of and find b accordingly. I will find the sign of Wt transpose xj plus b. If it is positive plus class, negative minus class. So, this is equivalent to sign of, if we substitute w value here, what you need to do is to just take the support vectors, and take the dot product of each of the support vector with the new point to be classified, okay, into yi actually, yi, xi, xj. So, yi, xi is the support vector, xj is the new point, compute the summation, add b, look at the summation, look at the sign of that, you get your classification of a new point. Okay. So, that is how you do it, all right. So, this is the simple thing, So, what I want to do is that, so there are actually many toolboxes. So, this is the pictorial representation of all I wanted to say. This will depict the values of alpha, you can go through the slides. Okay. So, wait, so I will go into that later. So, this is the characteristic. So, there are many softwares which can solve this problem, solve the QP and give you alpha i's, which you can use and do the training set. There are two more extensions to this problem. All my theory so far has been for two classes. Can I extend it to multi-class? And also I have affirmed that the two classes are separable linearly. What happens if they are overlapped? What happens if they are non-linearly separable? So, we will discuss that in our next lecture on when we extend into overlapping support vector machines, soft margin support vector machines and kernel machines, which are a non-linear version of the support vector machine. Thank you for today.